Nature has laws. Not suggestions, not guidelines. Laws. Gravity pulls things together. Energy is conserved. Cause precedes effect. These principles are so fundamental that the entire scientific enterprise is built on them. And then we look out into space and find things that seem to be breaking them. Not bending the laws slightly, not exploiting loopholes. Actually violating principles we thought were unbreakable. Phenomena that make physicists question whether the laws of nature are as universal as we believed. Here are 10 cosmic phenomena that appear to break the rules. Starting at number 10, we have galaxies rotating faster than gravity should allow. Galaxies are held together by gravity. The visible matter creates a gravitational field that keeps everything in orbit. The physics is straightforward. You can calculate how fast objects should orbit based on how much mass is present. Except when you actually measure galaxy rotation speeds, they're wrong. Stars and gas at the edges are moving way faster than they should be, so fast that they should be flung out into intergalactic space. But they're not. The galaxies hold together just fine. This is why dark matter was proposed. There must be invisible mass providing extra gravity. But here's the uncomfortable truth. We've never directly detected dark matter. We've never produced it in a lab. We've never measured a dark matter particle. What we have is galaxies breaking Newton's laws of motion and Einstein's general relativity unless we add invisible matter we can't see. Either there's a massive component of the universe that's completely invisible and undetectable except through gravity, or gravity itself works differently on galactic scales than we think. Both options involve breaking fundamental assumptions. At number 9, we have quantum entanglement violating locality. Quantum entanglement is one of the strangest confirmed phenomena in physics. When two particles become entangled, measuring the state of one instantly affects the state of the other, no matter how far apart they are. This seems to violate locality, the principle that objects are only influenced by their immediate surroundings. But entangled particles don't care about distance. Measure one, and the other responds instantaneously, even if it's on the other side of the galaxy. Einstein called this spooky action at a distance and believed it proved quantum mechanics was incomplete. But experiments have confirmed that entanglement is real. Bell's theorem showed that no theory based on local hidden variables can reproduce quantum mechanical predictions. The universe really does allow instant correlations across arbitrary distances. This doesn't allow faster-than-light communication, so it doesn't violate causality. But it does violate our intuitive understanding that space separates things in a meaningful way. Two entangled particles remain connected in a way that transcends space, and this connection is real, measurable, and fundamentally non-local. Number 8 is Hawking radiation violating energy conservation. Black holes trap everything, including light. Nothing escapes. This is the defining feature of a black hole. The event horizon is a one-way boundary. Except Stephen Hawking showed that black holes actually emit radiation and slowly evaporate. Virtual particle pairs pop into existence near the event horizon. One falls into the black hole, the other escapes, and from a distance, it looks like the black hole is radiating. Here's the problem. Where does the energy come from? The escaping radiation carries energy away from the black hole, causing it to lose mass. But energy has to come from somewhere. You can't create it from nothing. Hawking's resolution is that the black hole's mass energy decreases to provide the energy for the radiation. The black hole itself is the source. But this creates another problem: information. If a black hole evaporates completely, what happens to all the information about everything that fell in? Quantum mechanics says information can't be destroyed, but the black hole radiation is thermal and random, carrying no information about what created it. This is the black hole information paradox, and it represents a fundamental conflict between quantum mechanics and general relativity. At number 7, we have cosmic inflation, violating the speed of light limit. Nothing travels faster than light. This is a cornerstone of special relativity. The speed of light is the universe's ultimate speed limit. You can't exceed it. Period. Except during cosmic inflation. In the first fraction of a second after the Big Bang, the universe underwent a period of exponential expansion where space itself expanded faster than light. Regions of the universe that were once close enough to interact are now so far apart that light from one could never reach the other. This seems to violate the light speed limit, but there's a technicality. The limit says nothing can move through space faster than light. It doesn't say space itself can't expand faster than light. During inflation, objects weren't moving through space at superluminal speeds. Space between them was expanding at superluminal speeds. This is a technical loophole, but it's still unsettling. The practical effect is indistinguishable from objects moving faster than light relative to each other. And inflation requires this to happen. Without faster-than-light expansion, the universe wouldn't have the properties we observe. Number 6 is negative mass in the Casimir effect. Mass is positive. Everything has positive mass. Positive mass means positive energy. You can't have negative mass. It would have bizarre properties like accelerating in the opposite direction when you push it, violating Newton's third law. Except the Casimir effect involves something that behaves like negative energy. When you place two uncharged metal plates extremely close together in a vacuum, they experience an attractive force. This force comes from the quantum vacuum. Virtual particles normally pop in and out of existence everywhere, but certain wavelengths can't fit between the plates. This creates an imbalance, fewer virtual particles between the plates than outside, resulting in a net attractive force. Mathematically, this situation involves negative energy density between the plates. Not just low energy, negative energy. Less than the vacuum, less than nothing. This doesn't create negative mass objects you can hold, but it does show that negative energy density is possible in specific quantum configurations. And if negative energy is possible, then exotic spacetime geometries like wormholes and warp drives might be theoretically possible because they require negative energy to stabilize them. At number 5, we have time dilation violating simultaneity. Time is universal. When something happens, it happens at a specific moment in time, and everyone can agree on when it happened. If two events are simultaneous, they're simultaneous for everyone. Special relativity destroys this intuition completely. Time dilation and length contraction mean that observers moving at different speeds experience time differently. What's simultaneous in one reference frame isn't simultaneous in another. If you're on a train and flash a light at both ends, you'll see both flashes reach the middle at the same time. Someone standing on the platform will see one flash arrive before the other. Both observations are correct. There's no true simultaneity. Time itself is relative to your motion. This doesn't just mean clocks run at different speeds. It means the actual sequence of events can be different for different observers. Event A can happen before Event B for you, and Event B can happen before Event A for someone else, and both of you are right. This has been confirmed experimentally countless times. GPS satellites wouldn't work if we didn't account for time dilation. Time is not universal. Cause and effect depend on your reference frame, and this is just how the universe works. Number 4 is the second law of thermodynamics being violated by Maxwell's demon. The second law of thermodynamics says that entropy, disorder, always increases in a closed system. Heat flows from hot to cold. You can't spontaneously unmix a scrambled egg. This law is considered one of the most fundamental in all of physics. Maxwell's demon is a thought experiment that seems to violate it. Imagine a box of gas divided by a partition with a tiny door. A demon sits at the door and watches molecules. Fast molecules approaching from the left. The demon opens the door and lets them through. Slow molecules from the right, door opens. Slow molecules from the left, fast from the right, door stays closed. Over time, all the fast molecules end up on one side, all the slow molecules on the other. The demon has separated hot from cold without doing work, decreasing entropy, and violating the second law. For over a century, physicists struggled with this paradox. The resolution came from information theory. The demon has to observe molecules, which requires gathering information. Storing and erasing that information generates entropy that exactly compensates for the entropy decrease from separating the molecules. But the fact that we had to invoke information theory to save thermodynamics reveals something profound. Information is physical. The second law isn't violated, but its connection to information shows that the laws of nature are stranger than they first appear. At number 3, we have the Pauli exclusion principle making matter solid. Why is matter solid? Why doesn't your hand pass through the table? The obvious answer is that atoms in your hand hit atoms in the table and stop. But atoms are mostly empty space. The nucleus is tiny. The electrons are even tinier. If you scaled an atom up to the size of a football stadium, the nucleus would be a marble at the center, and the electrons would be grains of sand orbiting in the stands. Everything else is empty. So when your hand touches the table, it's empty space touching empty space. So why don't they pass through each other? The answer is the Pauli exclusion principle, a quantum mechanical law that says two identical fermions can't occupy the same quantum state. Electrons are fermions. When electrons in your hand get close to electrons in the table, they can't occupy the same space because the Pauli exclusion principle forbids it. This isn't a force in the conventional sense. It's not like electromagnetic repulsion. It's a constraint imposed by quantum mechanics that simply doesn't allow certain configurations to exist. The universe enforces this rule absolutely, no exceptions. The solidity of matter exists because quantum mechanics says certain arrangements are forbidden, not unlikely, not energetically unfavorable, forbidden. Matter is solid because nature has rules about what's allowed to exist. At number 2, we have vacuum fluctuations creating real particles. Empty space is supposed to be empty. No particles, no energy, nothing. That's what empty means. Quantum mechanics says empty space is actually roiling with activity. Virtual particles constantly pop into and out of existence, borrowing energy from the vacuum for incredibly brief moments before annihilating and returning the energy. This sounds like theoretical nonsense, but it has measurable consequences. The Casimir effect, the Lamb shift in atomic spectra, and the anomalous magnetic moment of the electron all arise from vacuum fluctuations. These effects have been measured to extraordinary precision. Even more remarkably, vacuum fluctuations can create real particles. In strong electromagnetic fields, virtual particle pairs can be ripped apart before they annihilate, becoming real. This is called the Schwinger effect, and it's been confirmed in high-intensity laser experiments. The vacuum is not passive, it's an active participant in physical processes. And in extreme conditions, it can create matter from nothing, not metaphorical nothing. Actual empty space with no particles, no energy, and no matter producing real particles with real mass and energy. And finally, at number 1, we have the universe creating something from nothing in the Big Bang. The ultimate law of nature should be that you can't get something from nothing. Existence requires a cause. If something exists, something must have created it. This is basic logic. The Big Bang appears to violate this principle at the deepest level. The universe began from a state of extremely high density and temperature and has been expanding ever since. But what was there before? Where did the initial energy come from? What caused the Big Bang? Some cosmologists propose that the total energy of the universe is actually zero. The positive energy in matter and radiation is exactly balanced by the negative gravitational potential energy. In this view, the universe isn't something from nothing. It's a rearrangement of nothing into positive and negative components that sum to zero. Others propose that quantum mechanics allows the universe to tunnel into existence from a quantum vacuum state. Just as virtual particles can briefly violate energy conservation, maybe an entire universe can. The most honest answer is that we don't know. Our physical theories break down at the Big Bang. General relativity predicts a singularity where density and temperature become infinite and the laws of physics cease to make sense. We need a theory of quantum gravity to describe what happened, and we don't have one. The universe exists. That's an observational fact. But the laws of physics, as we understand them, don't explain how something can come from nothing. Either the Big Bang represents a genuine violation of causality, or there's a deeper framework we haven't discovered yet that makes it make sense. 10 phenomena that break the laws of nature, or seem to. Some of them have explanations that preserve the laws by introducing new concepts. Others remain genuinely mysterious. All of them show that the universe is far stranger than our everyday experience suggests. The laws of nature might be universal, but our understanding of them is incomplete. Every phenomenon that seems to break the rules is an opportunity to discover that the rules are more subtle, more complex, and more beautiful than we realized. And that's what makes science exciting. We're not just cataloging facts, we're uncovering the hidden architecture of reality itself. If you're fascinated by the universe's rule-breaking behavior, hit that subscribe button and turn on notifications so you never miss an upload.